I think it's pretty much ready to go. I hope that's not bothering you. Okay.
Does anyone still need to find out?
Another thing. I don't think it's. Is your microphone port?
I think it's okay. I'll just shout. Yeah.
All right, everyone. So today we'll have Dr. Liu do a brief review of the principle of virtual work, and then she'll do a couple of examples. And maybe at the end of it, you can give us both some feedback on anything about the course in general. So turn it over to you, Hui.
Okay. Hi, everyone. So today, let's first begin with a quick review on what we have learned on the topic of principle for virtual work. The principle of virtual work is a more general method comparing to the real work, real energy. Okay, I'll try to speak up loud. Okay, so can you hear me now? At the back, perhaps? Yeah? Okay. So the principle of virtual work is a more general method comparing to the real work, real energy method, because using this method, you can express the unknown displacement at any point in terms of corresponding unknown forces to find out those displacements. And we have learned the method of virtual work to solve for truss problems and the beam problems. So for truss problems, you can just first apply a virtual force at any point of interest, and then find out the virtual internal forces of each member, and then find the real internal forces and real displacement of the individual members, and finally we can solve the delta using this method, using this equation. And similarly for the virtual work method of a beam, if you want to solve for some deflections, you need to apply a virtual force at that point, or if you want to solve for slope or rotation, you need to apply a virtual moment at that point. And then we have learned some applications of the virtual work method. This method can be applied to any problems as long as you can calculate the virtual work and virtual internal energy. The types of internal energies includes these few things, such as, for example, the trusses. It will be the internal virtual energy will be just the actual force times the displacement of each and individual member and the sum of it. And for the beam bending, we have learned that internal virtual energy will be the virtual moment times the real curvature and integration of the entire beam. And then for shear, we have this virtual shear stress times the real shear strain over the entire beam. And similarly for actual, it will be the virtual actual stress times the real actual displacement. And then we have learned torsion and temperature as well. So for torsion, first we need to know that the internal virtual energy is actually calculated based on this equation. So for if we look at the cross section, the torsion will apply some shearing stress on this cross section, and to calculate that internal energy, it will be the virtual stress times the real strain integrated over this area, and then integrated over the entire beam. So if we look at this cross section here, we can see that to calculate this delta the force over this small area, it will be just this sharing stress over this small area times the small dA, and that will give us CR over dA, where C is actually the radius of this cross-sectional area. And then the torque will be the integrals of the shearing stress times the R, which is the distance from the origin to this small dA. And then that gives us CR squared dA. And finally, we can see that the torque is equal to that. The J is the polar moment of inertia for a circular cross section. It will just simply equals to pi C4 over 2, and finally we can express this virtual stress in terms of the torque in this expression. So if we substitute that back into this expression, we have where here is the virtual torsional stress, well, times with the real, this part is the real torsional strain. And then finally, we can obtain this expression for the internal virtual energy for the torsion part. And also for the temperature change across a beam depth, we so if we look at a cross section of a beam, and there's a temperature change across the depth, where the top will be T1 and bottom of T2, and then we can express T1. The deformation of the top will give us this expression, where alpha, we recall that it's temperature constants that gives us the deflection equals to dt times alpha times L. So that's how we get the top part displacement. And then the bottom part we can express as dx plus alpha t2 dx. And if we calculate by that minus this, we obtain a 2c d theta alpha t1 minus t2 dx, and finally obtain a d theta dx equals alpha t1 minus t2 over d. And then we know that the internal virtual energy due to the temperature change will be the virtual moment times the real curvature will be this expression. So now let's look at some examples. Yeah. Oh, okay. I'm sorry. I'll take note now. Okay. Now let's look at the example here.
Can you go back?
Oh. So you all get that? Okay. So now let's look at an example here. So here is this beam. It's a T-shaped beam and subjected to two equal loads in an opposite direction at these two endpoints. And all members have a circular cross-section area A. And now we assume that the joint at B is rigid. And now it asks you to calculate the displacements at points C and D. And you have to take into account for bending, shear, and torsional deformation. Okay, so now I'll give you perhaps 3 minutes to discuss in group, and then we come back and solve it together. Okay? All right.
Oh, I mean, like, all these things. Yeah.
Okay, let's come back and talk about this example together. So now when we look at this problem, what do you think the deflected shape will look like? Anyone? Twisting, yeah. And because we have also considering the bending, so what will this member look like? Yeah, okay. So it will be look like something like that, right? Yeah. Okay. So to solve these problems, first let's look at the real response of the load. So let's look at it one by one. First is the shear response. The shear diagram will be just like that, right? That's -2 and 2 over here. And bending moment, what would the bending moment look like? Anyone? Yeah, triangle. It will go like that, right? And if we say x1 from left to right, we'll have, actually it's upside down. It should be -2 x1 and x2, then here should be 2 x2. And then finally, when we look at torsion, what would that look like? What is the torsion in this member? Is that constant or is that a triangle shape? What do you think? Yeah? What did you say? Yes, that's right. And that will give us, this is 2 feet, and 2K here. So each will give us 4K feet. So together we'll have 8K feet torsion in this member, constant. And then for the virtual part, so for virtual part, what kind of virtual forces are we gonna apply? What kind of forces should we apply? we're looking at looking for the displacement at C and D. So we apply virtual forces at these 2 points, right? That's right. P prime here and P prime here. And the shear force will be the same. It will look the same as the real part, minus P here, minus P prime here. And then moment diagram is the same as well. Now, what would be the amount for this constant virtual torsion? Say P prime and P prime over here. That'll give us 4 P prime, right? Yes.
Can you explain why you apply to virtual loads?
Because we're looking at the displacement at both C and D, right? So if we want to look at, find out what would be the displacement at a certain point, we will apply a force at that point, a virtual force at that point.
That would only work if it's symmetric. The displacements at 2 points are different. You can't apply two virtual loads and then find both the displacements at the same time.
So normally what we would do is that for each displacement we're looking at, we'll just apply one force at that point and solve using the same procedure again at another point. But however, if we look at this problem here, we can sort of intuitively find out that the displacement at these 2 points should be the same, right? Because it has the 2 equal spans, both are 2 feet, and both are applied with the 2 kips loading. So we should expect 2 equal but opposite displacement at these 2 points. So that's why we can apply 2 virtual forces at the, each point. Does that sound make sense to everyone? Yeah.
What would happen if you just did one? Like what question would you find?
You should get the same answer, only that you have double the procedure to solve this problem. Yeah. Okay. So now we have both real and virtual system with the diagram drawn, and now we can write out, apply the method of virtual work. Which is that virtual external work equals to the internal energy. And what would be the external work look like? So there are 2 forces. Yeah, that's right. That will be P prime delta C plus P prime delta D. And those 2 are equal, and so we can get and now for the internal virtual energy, first it will be a sum of shear plus bending plus torsion. For the shear part, we will have the integral over the beam, the virtual stress times the real strain Bending will give us the virtual moment times the real curvature. And finally, the torsion. And now that we equal this virtual external work to the sum of the internal energy, we will have and the two p primes will come to the right hand side. And finally, you can get this delta in this expression. Is there any question about this problem? Yeah? Oh. Other way? Okay. Yeah.
What's the last fraction number for it? I mean, 4p, yeah. 4p prime over DJ times.
8 times 4 and over 2p prime. So do we have any more questions about this example? If not, then let's look at the second example here. Okay. So here we have an L-shaped frame fixed at this end A and subject to a uniformly distributed loading at this member BC. And now it asks to find out the horizontal deflection at point C. And again, you have to take into account for axial and shear deformation as well, in addition to the bending. Okay? So now let's discuss, and then we talk about this example together.
So And then you apply C prime and X No, not yet. No, that's right. What do you Oh, okay. You hate Delta study? You hate Delta study? Yes. What did you guys PS or oh, you're PS guy?
Okay, everyone, let's come back and look at this example together. Okay, so first thing, what kind of virtual forces are you applying to this structure? Yes? P prime at which point? Yeah. A horizontal or, yeah, that's right. This one is pretty straightforward since we're just looking at one displacement at one point. And then, again, first we look at the real system. So first we need to draw out the shear force axial and bending moment diagrams. So first, the shear force diagram, what do you think it will look like? Let's look at the members one by one. For member BC, what will it look like? Yes, that's right. It will be and then the amount will be Wx, and here it will give us Wl. And how about this member? Yeah, that's right. This member will be 0 for shear force. And then for the actual forces, what will be the actual force in this member? 0? Yeah, that's right. How about this one? Yeah, WL. Positive or negative? Yeah, because it's a compression. Minus WL. And then lastly, the bending moment diagram. What will be the bending moment in BC?
Parabolic.
Yeah, parabolic. Okay. And what would be the value here at the end? That's right. 2. And how about member AB, the horizontal member? What would be the constant? That's right. Okay, so now we have the real system. And next, let's look at the virtual system. And the virtual system will just have one point load at point C in the horizontal direction. And for that system, what's the shear force diagram look like? With the virtual force at this point? Yes. It will be just P prime. And similarly for actual force, 0 in this member. And in this member? Yeah, that's right. Again, it's a negative because it's compression. Negative P prime. And bending moment in this member. Attract, yeah. Minus P prime L. And how about this member? Yes. Okay, now that we have all the diagrams here, so now we can apply the virtual method of virtual work. Internal. The external work is straightforward. It's just P prime times delta C. And for internal energy, again, it should be the sum of internal energy due to shear plus actual bending. Okay, just similar to what we have done for the previous example, what would be the shear part of the internal energy look like? Yes. Yeah.
So P prime A times K.
Over.
Oh wait, that's it. That's it. Just P prime times the actual.
So it will be first the virtual stress, right? Okay. Let's first write out the full expression. The virtual stress will be V prime over A, and of course, if we consider the shift factor K, and then times the real strain. What would be the real strain? Yeah, that's right. And then times A. And this 2A will be canceled out. And that V gives us omega X. And now if we do integration over L to 0 to L, we will have P prime so that's the internal virtual energy for the shear part. Now what would be the actual part? Of course, it will be integral from 0 to L. What's inside? The virtual stress. Yes. What will be the virtual stress? M prime over A times the real strain. Yeah. These two cancel out again, and that minus so that will give us the actual part of the internal virtual energy. And lastly, the bending part. Bending part will be the virtual moment times the real curvature. Since we have the moments in both members, so we need to calculate one by one. So this will be x1 over the second member is also from 0 to L. Okay. So for member BC, what would be this M prime? That's right. P prime x1. And how about the curvature, real curvature? Yeah. And then for this member, the virtual moment will be just P prime L since it's constant. And how about the curvature, the real curvature? Yeah. And then now let's integrate both members. Plus P prime omega LQ. And lastly, we can equate the external work with the sum of the internal energy. We will have and again, the P prime will be canceled out, and then we'll have the final expression for delta C. Now, is there any further question about this example? No? Is it clear to everyone? Okay.
Since there's only 4 minutes
Yeah.
left,
Oh, okay.
maybe instead of the last example, I was thinking that you guys can do an in-class assignment that I just thought up of. Oh no, yeah, that's right. We have a spare sheet here. Oh, okay. Oh, there we go. All right, so in-class assignment, please take out a piece of paper, write your name on it, and you will not be able to finish that end to end. So just set up the problem, WE and UI prime, and that's all we are looking for. So it's practically the same problem. Instead of that wrench, we have just one leg, and I think you have the numbers on that. Yeah, 2 kips. So this is 2 kips. This guy is 4 feet, and this is 2 feet. Everything else is exactly the same. Using principle of virtual work, what is WE prime? What is UI prime? The problem is we want to find displacement. Let me label them the same way as well. A, B, C. And we want to find delta C. Okay. So that's the problem. And as a supplement, I would also like you to provide feedback for DrLiu or for me on anything that you think we should do better in terms of teaching. Okay, so similar problem, just write what W, E prime and UI prime should be and give some feedback to us. And that will be your ticket out the door.
You want values for U prime?
What's that?
You want values?
I don't want values, just set up the integral. Just set up the integral, but of course to set up the integral you would have to write the correct expression for what is the bending moment, what is the torsional moment and all that. You don't need to do the integrals themselves, but you need to set up exactly like the example. 1 minute, okay. I guess we don't have enough time for this example, but do what you can, and I think feedback would definitely be helpful.